In 1793, France was in the throes of revolution, having just executed Louis XVI. She was now besieged by all the major armies of Europe, threatening to invade and extinguish the tottering new republic, and thus prevent the so-called American conditions from emerging in Europe. With the entry of England's naval might into the war, France was being starved into submission via a blockade. Revolts in Vendée, Toulon, and Lyons were being fomented, and with the defection of Dumouriez, the commander of the French Northern Army, to the British, a complete disintegration of the French army ensued. Into this maelstrom, the mathematician, physicist, and revolutionary Lazare Carnot was elected to the notorious Committee of Public Safety, in charge of military planning. The Committee of Public Safety would go on to instigate the Reign of Terror under Robespierre. Yet the election of Carnot and his genius for organization would prove to guarantee the survival of the Republic. He would later be known as the organizer of victory. It could be said that Carnot invented modern industrial warfare, with mass armies, conscription, strategic logistical planning, and the creation of an industrial military scientific research program. He employed the brightest scientific minds of France to reform and support the French Revolutionary Army, which went on under Napoleon to conquer all of Europe.
20 years earlier, Lazare Carnot, while studying under mathematician Gaspard Monge at the military academy in Mézières, met another revolutionary and scientific genius, Benjamin Franklin. In 1784, he published his first scientific work, entitled Essays on Machines. This book contained the earliest proof of the non-conservation of kinetic energy during the collision of imperfectly elastic objects.
It also set out the principles of energy conservation. This work could be said to foreshadow the work of his famous son Sadi Carnot, who is known as the father of thermodynamics. Sadi was born only 3 years after Lazare's election to the Committee of Public Safety. He was named by his father after the famous Persian poet Sadi of Shiraz. At the age of 27, in 1824, he produced his singular scientific masterpiece, Reflections on the Motive Power of Fire, which in its discussion of the efficiencies of heat engines laid the groundwork for the field of thermodynamics. He died tragically of cholera only 8 years later, in 1832, the same year that his father died, now in exile for his role in the regicide during the French Revolution. Initially, Sadi's work were completely overlooked during his short life. However, by 1834, his work was used to derive the concept of entropy and the second law of thermodynamics. Sadi's work was motivated by a desire to improve the efficiency of steam engines. Thus, thermodynamics was originally concerned with the behavior of heated gases and their ability to perform work. From this sprung the understanding of physical laws governing energy and order. The most important of these were laws that related to the symmetry of the distribution of a given gas, to the energy that could be extracted. So, for example, if there was a system where one container held a hot gas and another a cold gas, the heat differential could be used to drive a so-called heat engine and extract work, like driving a piston of a steam engine. However, once the system was thermally mixed so that equilibrium was attained, then no more work could be extracted. The new concept of entropy quantified this symmetry of mixing. A system would be in the highest entropic state when it is most symmetrical, that is, when the hot and cold gases are perfectly mixed. Thus, if one samples the gas at any point, one would find an equal number of fast or slow particles. Conversely, the lowest entropic state is one where the hot and cold particles are distributed as asymmetrically as possible, the fastest particles completely separated from the slow. The concept of entropy was introduced, along with the second law of thermodynamics, which related the rise of entropy to the extraction of energy from a given system. In this context, the change in entropy was defined mathematically by the ratio of the change in energy to a fixed temperature. Yet, at the very inception of the field of thermodynamics and the concept of entropy, a profound problem was made evident. It was none other than James Maxwell, the father of electromagnetic theory, who had devised a thought experiment that challenged the ideas enshrined in the second law of thermodynamics, specifically the idea that for a system of particles in thermal equilibrium, where all the fast and slow-moving particles were completely mixed, that no more work could be extracted. Maxwell imagined a box containing this distribution, with a wall dividing it into two sides. In the wall there is a door, which is controlled by some demon that could open the door only for fast-moving particles and keep it shut for the slow ones. In this way, over time, all the fast particles would come to reside on one side of the box, leaving the slow particles on the other. In this situation, a heat engine could be run from the differential in temperature, thus extracting work, in apparent violation of the second law of thermodynamics. For many years, Maxwell's demon challenged the understanding of entropy and the second law.
At first, some thought the energy used by the demon to open the door and thus sort the particles would resolve the problem. Yet, it wasn't until the merging of the new field of information theory with thermodynamics in the mid-20th century that this paradox was finally resolved, and the Maxwell demon was understood to be what is known as an information engine, a machine which creates work by creating information. This solution required the understanding of the physical nature of information,
manifested as symmetry breaking of some physical system.